Hey everyone, and welcome. Today, we're going to demystify a statistical technique that seriously feels like a magic trick. It's called bootstrapping, and let me tell you, it is an absolute game changer when you're dealing with messy, real-world data. So, just imagine this for a second. You've collected some data, but there's a problem. Maybe you've only got a tiny little sample. Or maybe when you look at it, it just seems weird. It's not that perfect, clean bell curve that you learned about in stats class. So, what are you supposed to do now? Well, see, the problem is that a lot of the classic statistical tools have a whole bunch of rules. They kind of assume your data is going to behave itself, that it follows a nice known pattern. But let's be real. Data from the actual world is often messy, it's unpredictable, and it almost never fits into a neat little box. And that is where bootstrapping saves the day. Don't think of it as some scary, complicated formula. Oh no. Think of it more like a brilliant hack. It's this clever, modern workaround that uses the sheer power of our computers to get us reliable answers, even when our data is being super difficult. Okay, so let's get the official definition out of the way. There are two phrases here you really want to lock onto. First, computer intensive, which just means we're going to let our computers do thousands of calculations for us in the blink of an eye. And second, distribution is unknown. And that's the whole point. Bootstrapping doesn't care if your data looks strange. It was literally built for those messy real-world situations. And the name itself is pretty cool, right? It comes from that old saying. The whole idea is that you're using only the data you already have and absolutely nothing else to learn more about that data. You are, in a very real statistical sense, pulling yourself up by your own bootstraps. And here it is. This is the core assumption, the big idea that makes this whole thing work. You make a really simple but incredibly powerful decision. You decide to treat the little bit of data you have as if it's the best possible picture of the entire universe of data. By just assuming your sample is the population, you unlock this amazing new way to learn from it. So, how do we actually do this? How does it work under the hood? Let's dive into the process, because it's a super logical, step-by-step thing that all hinges on this idea called resampling. The whole thing really breaks down into these 4 steps. First, like we just said, we pretend our sample is the whole population. Second, and listen up, because this is the magic part, we resample with replacement. That means we create thousands of new samples by picking from our original data, but every time we pick a number, we put it back in the pile before picking the next one. This means some numbers might get picked a few times and some might not get picked at all. Third, for every single one of those new samples, we calculate whatever it is we care about, say the average. And finally, we just gather up all those thousands of averages we calculated and look at the new pattern they've created. All right, let's stop talking theory and look at a real example. Here's our original sample, just 10 little numbers. This is our mini population that we're going to play with. Now, if we calculate the average or the mean of this group, we get 17.4. Just kind of tuck that number, 17.4, in the back of your mind for a sec. Now we tell the computer, hey, go grab 10 numbers randomly from our original list. But remember, it's with replacement. So look, see how the number 15 and the number 21 got picked twice? But wait, where are 17 and 20? They didn't get picked at all. That is resampling with replacement in action. It creates a new, slightly different sample with a slightly different average. And let's do it again. Here's a second bootstrap sample. Totally different mix, right? Now we've got 19, 14, and 22 showing up twice, and different numbers got left out this time. Each new sample is just another random shuffle of our original data, and each one gives us a new mean. But here's the thing, we don't just do this a couple of times. A computer does this for us thousands of times. It creates thousands of these unique little bootstrap samples, and for every single one, it calculates the mean. What we end up with is this brand new, massive data set made up of thousands of possible sample means. Okay, I know what you're thinking. Why on earth did we just do all that? What's the payoff? Well, all of that work lets us build something called a confidence interval. You can think of it as a range of plausible values. See, we know the mean from our original little sample was just an estimate. A confidence interval gives us a much more honest and reliable range of where the true mean of the entire population is likely to be. And the best part? The way we actually find this range is so simple. It's called the percentile method. I mean, we just created a distribution of thousands of possible means. So it kind of makes sense that the true mean is probably going to be somewhere in the middle of all those possibilities, right? So we just have to find that middle chunk.
Check out how beautifully intuitive this is. If you want a 95% confidence interval, you take all those thousands of means you calculated, line them all up from the smallest to the biggest, and then you just chop off the edges. You lop off the bottom 2.5% and the top 2.5%. The range that's left over, that middle 95%, that's it. That's your confidence interval. It's that simple.
All right, so let's zoom back out and put it all together. Now that we've got the what and the how, let's just do a quick recap of the when. When is this the right tool to pull out of your toolbox? You should be reaching for bootstrapping pretty much any time you find yourself in that messy situation we talked about at the very beginning. When you have no idea what the shape of your data is, when your sample size is tiny, when you just can't meet all the strict assumptions of those older statistical tests, or when you're trying to measure something really, really complex.
I mean, the advantages here are just fantastic, right? It's so flexible because it makes zero assumptions about your data. It's incredibly powerful because it works for almost any statistic you can think of. And thanks to modern software, it's actually super easy to do and to understand what you're looking at.
And that kind of leaves us with this one big, exciting idea. Bootstrapping is the perfect example of how pure computing power lets us completely rethink and sometimes even just break the old rules of statistics. It really makes you wonder, as our technology gets even more powerful, what's the next fundamental rule we're all going to challenge? And what incredible new insights is that going to unlock for us? Thanks for hanging out and geeking out with me on this one.